Okay. In our previous presentation, we talked about waves as disturbances that transmit energy from one place to another without the medium actually moving. I think the explanation we made there was adequate. So, but people complained about the diagrams. So we were giving example of oscillatory systems that are capable of doing work from afar or transmitting energy into or over long distances by oscillation, because waves themselves are oscillatory. As you can remember, we decided to make these presentations in order to debunk the fallacy that 5G networks are responsible for the novel coronavirus disease that is disturbing the world right now. Here is a spring mass system. This is a spring. So a mass is attached to it. So let's say this is the equilibrium point, as we call it, the point of balance. If you pull this mass, increasing the length of the spring by extension E, then upon releasing it, the mass will keep oscillating. That oscillation in a perfect vacuum, we said yesterday, according to Newton's laws, in a perfect vacuum, this oscillation will continue forever. But in a real situation where you have air and the surrounding, air resistance, because this mass M will be doing work, will be transferring the energy stored in the spring to the to the surrounding. So what we have here is the motion will ultimately stop, because the forces that are going to stop the swinging pendulum or the swinging string, the swinging mass on a string, is called damping force. When something is dampened, as we said yesterday, it is called an inactive. So, for instance, let's consider, say, it's a vertical spring system, mass spring system, because all of oscillations are a result of the elastic property of materials. An elastic property of a material is that property of the material that enables the material regain its original shape after being displaced. So if here was the equilibrium position and you decided to compress the spring to this point, so and you have a ball here, a ball sitting here. Upon the compression of the spring, it will not stop at the equilibrium point, it will pass, so it will hit this ball. So if you keep compressing the spring and putting balls, you see balls running out, like the way maybe sacks of garin danwake will come out of gut mills, danwake milling factory machine, whatever. So this is mass spring system. I think my work now is not just it's not about a new something, but making the diagrams clear. This one I want to make it also very clear that it is also the same thing as if you suspend a mass and you pull it to a distance A. When you release it, it will not stop at the equilibrium point. It will make the same distance A on the opposite side and come back. So this also in a perfect situation will continue forever, but air resistance will dampen the motion. So The other one, we say, if you want to see waves propagating, I will leave the electrical circuit because it is our major concern. So I will treat it afterwards. So this electrical, the next thing we have is, we say a flame from a candle, from a gas cooker, whatever, connected, heating one end of a homogeneous iron rod. So this heat will be transmitted to this point by one molecule being energized, accelerated. It will hit a neighboring molecule and come back. Then this molecule will hit its neighbor and come back. That way, the kinetic energy supplied by this flame reaches point B from point A. So these were some of the diagrams we presented in the previous video. The other diagram is the simplest way you can explain waves, especially mechanical waves. Assume this is a still pond of water or a swimming pool in the morning. Nobody touches it. So there is a surface tension that makes it just still. We say a still pond of water. So if you want to disturb this system so that energy goes in many directions, just simply throw a stone. The stone will dent this line, like displacing the pendulum from its equilibrium point. So this line has been displaced from equilibrium points by an amplitude A. And here you have an amplitude A. And this will, upon going back, this will not stop at the equilibrium point. It will also make A in this direction. So also the water will make A in the opposite direction. Another A. Without damping forces, this will also continue forever. But this one single stone that you put to drive the wave, we call it an impulse. We have said that yesterday. An impulse or impulsive force or whatever, but we call it an impulse. So remember, this is work traveling, work being carried along by the wave, and the wave will do work on the barrier. If this is a building, if it is a concrete building, if it is a ball, it can get heated, it can get broken if the wave is strong enough. So if you want the wave to continue, we have free oscillations. Free oscillations damp down. They die down of themselves because of damping forces. But wherever you want a system to continue moving, for instance, the mass spring system, you have to be giving it a little pull at any time. So the frequency with which you pull will be the frequency of the wave. And we were talking about amplitude. We discussed amplitude actually is the maximum displacement of a system from equilibrium point. So this is the electrical analog of those things we said earlier. It is called RLC circuit. R for resistance, L for inductance, and C for capacitance. So this also works that way. This is also a state system. Maybe if you charge this capacitor before you put it, for instance, capacitor carries electric charges. Okay, RLC, we call it RLC, but it doesn't matter which one comes first. But let us follow the nomenclature. So, in this case, if you charge this capacitor, let's say having positive charges piled up on this side, you will have negative charges piled up on this side. So if you have a key, by the time you close this key, this capacitor will discharge in form of current, and as the current flows through this, it will produce magnetic fields perpendicular to the direction of this electric field. So these magnetic fields are said to be pointing out of the board. So this system will also die because this is the load, this is the resisting force, this is the damping force in this electric circuit. So if you want it to continue, you have to be applying an impulse voltage. It may be in form of alternating voltage. Alternating voltage probably given by V naught sine omega t. Time dependence. We are not going to talk about much of mathematics, but by the time you continue giving forth and back, it's just like pushing that pendulum, or you have a key on a pulley, so you are pushing the key. So the amplitude and the force, you are driving the oscillation. So this is also a driven RLC circuit. This is what we call series RLC circuits. We will talk much about RLC circuits later. So these are the diagrams that were not very clear yesterday. So we try to make them clear. As I told you, that the systems, the mass spring system, the mass spring system, the mass spring system, the pendulum, the heat transmission, the RLC circuit, and even the pond of water, they have the same equation of motion. We are not going to put equations here, but they are all second order differential equations. When we come to be technical, we are going to talk about that, but here we are trying to pass message to everybody. Thank you very much.